Well, it's a thrill to be in the PCD seminar. I think of it as Terry Winograd's seminar still. I think it's my third time here, though he's certainly put it into good hands. So thank you all for coming. Today, my subject is text visualization and their combination. So what do I mean by that? Well, first of all, I want to say that I have been thinking about problems at the intersection of text and visualization for a very long time. So here I'm showing some work from my PhD dissertation in 1995, which was 30 years ago, where I was looking at, does it make sense to show visualizations of search results where the visualization is showing where the query terms appeared in the document with different linked documents. More recently, I worked with Agarwala on linking visualizations to the references to them in text. So this has been an area of interest to me for a very long time, and only recently have I been trying to start thinking about what may be the cognitive underpinnings for these things, but it stems from never understanding why visualizations didn't work for search results. So I've been thinking about this for a very long time. So the structure of my talk is it's all about the combination of text and visualizations, and it has three main parts: how to combine the two in design. Then I'm delving into what do cognitive models tell us, but I got to warn you, I'm not an expert on cognitive models, so I've done a bunch of reading, but many people here probably know more than I do. And then finally, because you have to talk about LLMs, how does this relate to multimodal or visual LLMs? Another area where I'm not an expert and just did some recent diving into the papers. So again, that's my caveat for those parts. So let's talk about the first part, how to combine the two in designs. So first of all, what is information visualization? Visualizations are external visual representations that are systematically spatially related to the information they represent. And what are they for? This is a very famous example of a visualization called Anscombe's quartet. And what it shows are the same data with the same sufficient statistics, but with radically different plots. So the X has the same mean, the Y has the same mean, there's the same correlation and the same variances across all of these data sets, but yet they're radically different in their view. So it's a common argument made for why should we visualize data, the spatial relations that can be determined, which are not visible in just sufficient statistics. So we use visualizations to provide insight about data. But what I'm really interested in is what is the role of language with visualizations? And it's, until very recently, been a very underexplored question. In fact, some years ago, Apple released design guidelines for their web pages, and among those were design guidelines for charts. And if we zoom in to the design guidelines for charts, they talk about grid lines, plot area, marks, ticks. There's no title, and there's no text annotations. So they didn't even think to put in the design guidelines for text. That's how unrelevant text has seemed to the visualization community, for the most part. However, there were some results showing counter to this. So this well-known paper, Beyond Memorability, where the authors had a lot of people look at a lot of designs and then see what they remembered from the designs, found that the titles got the longest fixations during the encoding of the charts and were the most likely to be mentioned during recall. And this was followed by the label and the paragraphs. So clearly, when people are, even when they're having these visualizations flashed up at them very briefly, they are really looking at the text. So the main takeaway overall is that language is a key component of visualization, but we really don't understand how they should interact. All right, so for a given message, what should we express in text and what should be expressed as a visualization? What should be the balance between the two? Okay, so we have to first decide where should it go, what kind of text should it be, and how much information. So in this work, we started with some work that Marti Agarwala is a co-author on, where the research question was, what parts of a chart are attended to, are most salient, and to what extent do captions influence what people take away from the charts? And what happens when the text highlights the parts that are not the most visually salient? So here, the red parts outlined in red are the most, they've computed, are the most salient visually. then the green, then the blue. And they artificially created a whole lot of charts with these properties. And they then would have a caption like Macron's approval rating steeply dropped between June and August 2017. And so they found that when the captions and the salient parts aligned, participants, when they were asked to say, what do you take away from this design, they most often talked about the visually most prominent feature. But when the caption reflected the second or third most prominent features, the takeaways of the content of the caption were mentioned more than the most visually prominent feature. But when the caption reflected a non-prominent feature, the takeaways relied more on the chart. So when the two aligned, people talked about the alignment, but when the caption was not aligning with the most salient features, it kind of won out. But when there was no alignment of the caption to the features at all, then the features won out. So we're seeing an interplay between the language and the visuals, and sometimes one is more dominant and sometimes the other, and it's very complex. Okay, so second, what kind of text? So some work was done by Lundgaard and Saranarayan, looking at, they were actually interested in accessibility of visualizations and kind of what sorts of alt tags to make to describe visualizations for blind and low vision or BLV people. And they had people label a bunch of text captions, and they put the captions into 4 categories. I won't belabor the details so much, but into 4 categories. And there was a high-level category, which is reflecting external information about a chart, like the big drop in prices was caused by the financial crisis of 2008. So bringing in information that's not actually in the chart is the highest level of text. And the next level is text that talks about trends, like prices fluctuate but nevertheless increase over time. And then lower level, L2 was lower level, like just mentioning the value of a point. And they compared the views of blind and low vision people versus sighted readers to determine which levels they preferred to have augmented on a visualization. And they had a very interesting result, which is for the higher level descriptions, the majority of the BLV folks opposed those, but the sighted folks favored them. And for the low-level descriptions, the VLV folks favored them, and the sighted people were opposed. And they can imagine this makes sense, and that the sighted readers can see these details, and so they want to have the additional information, which perhaps is not serving the needs of the BLV folks. So I think this alone is a really interesting result. But they also concluded from this work that natural language should be seen as co-equal with visualizations in designs of visualizations. And again, this is a pretty radical perspective, or it was a few years ago in the visualization community. Okay, so now we have where are the salient parts of a graph, what kinds of text should be put on a graph. Now we'll talk about the work I did with my collaborators on how much text should be on a graph or a chart. So what we did was vary on a dial from charts with basically no text to just a title, to title, annotation, subtitle, lots of text. And we compared to a no chart variant, which was also not very common in information visualization research, because the prior work I'd done and also my intuition suggested to me that some people might not want a chart at all. So to do this work, we first identified the visually most salient regions of the chart using the work that Manish and others did earlier. And then we took these levels of text that were done by the Lundgaard and Saranarayan work, and we basically arranged them in different locations all over the place, working with a professional designer to help with the placement of the text labels and the annotations. And so we varied whether or not something from level 2 was in the title, or level 4 was at a point or on a trend, and so on. So we did a full experiment design with variations on these. So I'll ask you for your view, which of these was most preferred when people were asked to rank which ones they liked the best? I'll just take a show of hands. Give your own preference if you like. How many people prefer A? Okay. How many prefer B? Okay. How many prefer C? And how many prefer D? A little hard to see. Okay. Well, you are the same as the participants, except for nobody said the alt text, although I don't know if I gave you time to read it. So yes, what we found was more text is better. And in fact, the original title of the paper was something like under and over texting, and we never got over texting. And so we had to change it to striking a balance. But we see that there's a significant minority of people, by the way, who did not want the chart. There was also a small minority that didn't want any title, any text at all. And just like here, a fraction of people liked a little bit, but not too much. But actually, people really want to have a lot of text. And again, this challenges Tufte-esque minimalism, or just generally there's a lot of emphasis on minimalism in user interface design, and this challenges that. Sorry? Yes, we did actually, in a different study, which I will cover, but we did ask that too. I actually just don't quite remember for this. Usually it's a comment about, I don't need that to understand it. But I have some actual quotes in a second example. By the way, these results were reproduced by other researchers for other chart types. You've got the same preference information. They also did multilingual, but I don't have time to talk about that. Okay, so we found that rather than minimizing ink, we should annotate charts with relevant text. What is relevant text? The best position for annotation depends on the type of semantic level. So it wasn't really clean. It wasn't always L4 should go in the title. It was much more complex than that. Proximity of text to relevant visual components influences the takeaways, which makes sense. You want to have the annotation, say, about a point be near the point. And the best semantic level depends on the intended takeaway as well. So the other parts about what was best for what were a little bit messier. Okay, so now that takeaways are, we asked people, what did you learn from this chart? We asked them, what did they remember, actually? So another piece of work we did was we looked at predictions, which is different than takeaways from visualizations. So we started with a chart like this. So take a look, market share of two technology companies, blue versus green, and there's an event day coming up. How many people think blue will be higher when we get to the event day? Show of hands. And how many think green will be higher? Show of hands. Yeah, so it's about 50-50, which is the intention of the design here. So it's designed to be ambiguous. And there's another version with bar charts where the blue is always higher, but the green is always increasing. And so it's very much personal visual preference, which people choose to think is going to win. So it's a prediction problem. So what we wanted to do is see if we put text on this, would it influence people's predictions? So for example, if we put green, something about the green here, like green market share increased steadily and nothing about the blue, would more people switch to thinking green would win? What do you think? How many people think people switched their views when we put text like this on? And how many people think they didn't switch their views? So your hypothesis was the same as ours. People did not switch their views. Really interesting. And when I get to the cognitive part, I'll talk about why this might be, but we were surprised. And so, so we found that viewer predictions were largely unaffected by text annotations. So then we decided to ask another question. Oh yeah, in the case of visual predictions, the visual perception seems not to be swayed by the textual information. So then we decided to ask about perception of bias. So if we put this label, because like the text must be doing something, right? So if we put the text here, the green market share increased steadily, we expected people to say that maybe a green author wrote this and maybe they're biased towards green. And sure enough, we did find that was the case. And yeah. And by the way, I know this is kind of a mild statement, but we did try this with like more extreme statements like, go green, go, you're the winner, that it didn't make a difference with the first study. Okay, so this is pretty interesting. Viewer predictions largely unaffected by text annotations, but text provides a strong signal of potential bias of the author. So this is another example of the complexity of text and viz together. All right, so now the last piece of this I'm going to talk about are comparisons. And comparisons are super interesting because we make comparisons both with language and with visuals. So in the language, and in both cases, authors say that it's complex. It's very complex. Comparisons, how they're expressed in language is very complex. Comparisons and how we're expressed with visuals are very complex. So here's an example of a comparison from camera ranking data. I felt more comfortable with XTI, and some of my friends felt more comfortable with D80. So like, what is this comparison saying? It's very nuanced and subtle, like which is better. It's actually talking about comfort and friends. On the other hand, I actually prefer the D80 handling with smaller lenses, which is what's on my camera 80% of the time. So if you wrote back in the old days when we had to write programs to do process NLP, if you kind of try to do a word extractor to see, is this person favorable towards D80 or not, you would have a very hard time because the way they're expressing their preference is very subtle. In visualization, we do visual comparisons via juxtaposition, superposition, and explicit encoding. And something to note is in visualizations, we can compare a very large number of data points at a time, but with text, we can only compare 2 to maybe 5 if we use the word respectively. All right. So when we combine the two, what happens? So we did a piece of work where we wanted to, this is when I was collaborating with people at Tableau Research, and they wanted to make, they were making a tool where people could ask questions of data, and then they wanted to show visualizations as answers. So if you wanted to say, show me all the tall buildings, and we have a distribution, what is tall and what is not tall? That was the question. So this is something that people study in computational linguistics. And this work done, this is computational cognitive linguistics. These authors found that it depends on the shape of distribution of heights, what somebody will label with the vague word tall. And in fact, if we compare these 3 distributions, this one that's a very gradual increase versus one with one sharp step versus one with several plateaus, this is the predictions of the percentage of people that will say where tall begins. And so it's kind of flat, but then there's disagreement about exactly where does tall begin here. Here, there's a lot of agreement because there's a big jump. And then here, it's a little harder, again, because the steps, does tall start here? Does it start there? Disagreement. And so it's not about the height, it's about the relative height for a collection of items. And even if they were presented in the study, they weren't sorted even, but that's what people do. So what we did was we used this finding from cognitive linguistics to determine the bars to highlight for a visualization query. So if we have a query show the heights of the tallest buildings, and this is the distribution of all the buildings, using the calculation of what is tall that was simulated according to the simulation, according to the distribution in the prior work, we use that to determine which bars to highlight to mean tall. So this is an example of computational linguistics, cognitive linguistics in practice. So another comparison example I did as part of this collaboration is there was the Tableau folks were interested in putting visualizations in a chat interface. This is before modern chatbots, but in an interface where you were chatting back and forth on a mobile platform. And again, I suspected that people wouldn't want visualizations in a lot of the cases. And again, that was not what everybody else thought. So, and we started with these very simple comparison questions. Are there more events in weightlifting or taekwondo? So you're asking the bot that. And the bot answers, weightlifting has 15 events compared to taekwondo's 8. So it could have just said, there's more in weightlifting, but it's being a little more helpful than that. We could also augment this with 2 bars, one for the value for weightlifting and one for the value for taekwondo, or that might be seen to be out of context, so we can show those answers in context. So let's again get the preferences of the audience. Who prefers the first one without any bars? How many people? For if it was on your phone kind of thing, okay? Who prefers the second one? And who prefers the third one? Okay, you reflect what we found as well. So we found that more bars was preferred over a few because of the context. But 41% of the participants did not want to see the visualization in this situation. So now getting back to James's question, yeah, they preferred this. So what are some of the reasons? So for charts, Those that preferred more bars over a few, people said things like, at first I thought I wanted a simple answer, but after seeing more bars, I realized I really like getting the answer in context. And for text, they liked the simplicity and felt the charts were extraneous. They said things like, it's precise and gives me enough details without too many details or too few, and it was the easiest to understand, and the answer was not overly complicated. So those were the kind of answers we got. But we did have people look at multiple of these, and a few of them switched. And when they switched, so one person before switching said, the line graphs offer too much information, but on a second example, they changed their mind and said, in this situation, I think bar 3 is better because it shows us a graph. I think it's necessary because we are comparing stats rather than asking for a specific one. And I actually think the real reason was that it was information that was surprising that people weren't familiar with, and so actually seeing the bars in context gave them extra information they didn't need in the first case. So with a lot of these sorts of things, with language, it's very sensitive to the actual task. But we're still seeing very rich, complex, differences of opinion and differences in circumstances. So James, I hope that kind of answered you. Yeah. Okay, so to summarize this part of the talk, combining the two, text and visualizations, is complex. Findings from cognitive linguistics could be relevant in some cases, and comparisons are a really interesting case study. All right. So now I'm going to talk about text alone. So we've already seen 2 examples of text alone being favored by sizable minorities of participants, 41% in the bot example, 14% in the visualization of a kind of rich data example. Are there more examples in the literature? And it turns out there are, where people actually took the time or made the choice to look at text alone. So some work by Otley et al. Comparing outcomes for Bayesian reasoning. This I think was doctors. So text alone, where there's one of these, you have to figure out what choice to make, versus a visualization where they tried to show the proportion of points that were in the different conditions. And what they found was that there was no significant effect on accuracy for the different views. But when text and viz were presented together, the participants did not seem to take advantage of the distinct affordances of each. They seemed to pick one or the other and really focus on that. So again, kind of interesting. And she said, we currently do not have guidelines that maximize the impact of these two together. Another study was, if you're familiar with the You Draw It visualization, the New York Times, they were trying to see why that thing worked. But all you need to know is people were they needed to predict data, and they were comparing how well people recalled data depending on whether or not they made predictions. But they used both a visualization and a text condition in this case. And they found that presenting statistics as text helps people better recall the specific values later, but the visualizations help people better recall the trends than the text did. And seeing one's prediction against the observed data is helpful only if you're using the visualizations and not with the text. So this is kind of reminiscent of what we found with the predictions for the 2 charts that were kind of 50-50, was for predicting a trend, the visualization would be more salient. But it's not just, so that was that. Okay, so, and there's one study I didn't talk about, but overall, we're finding a lot of evidence that one should at least consider a text-alone option when one is designing an information display that includes visualization. And so that's that. And since we kind of started promoting this, we have seen more of this in the research literature. All right. All right, so that's the first part of this talk. So as you can see, there's a lot of conundrums that it raises. So I want to talk about, what do cognitive models tell us? Again, reminding you that I am not an expert on cognitive models, so if I say something naive, you can just correct me in the question section. But I actually want to talk about it from 2 angles. And the first thing is about reading, which is a little different than what I've been talking about so far. But I'm going to show you a visualization. I'm going to show you a screen. And what I want you to do is look at it and try to read the text. How many people found themselves distracted by the visualizations in the middle of the text? Yeah, basically everyone. So those of you who raised your hand may be guilty of doing this in your research papers, because we've noticed a trend now where people are starting to put big icons in the middle of the paragraphs of text. And from what I know about fluency in reading, it's probably not a good idea because it attracts your eye. I don't have proof yet, but we're starting some research to try to prove this because it's been something I've been saying for a while. So why is this? Well, again, I'm not a total expert on the psychology and physiology of reading, but I know a bit. And I really recommend this book if you want to know just the basics in a high-level way. Proust and the Squid by Marianne Wolf, who's a reading expert. And part of what she says is we were never born to read. It's an acquired skill. It takes a lot of education. And reading researchers have gathered extensive evidence suggesting that the processing of words occurs in the paraphobia before the word is directly fixated on. Paraphobia is like where you're looking at what you foveate on. The paraphobia is around that. And Wolf notes that the preview of what lies ahead makes what follows easier to recognize, contributing to the automaticity which aids fluent reading. So if you see the first few letters and you're kind of seeing the rest of the letters in the word in your paraphobia, it helps you recognize the word. And fluency does not ensure comprehension. Rather, fluency gives enough extra time to the executive system to direct attention where it's most needed, to infer, to understand, and predict. So what I'm arguing is we can read text, pieces of text, but if we want to get fluent with paragraphs of text, which all of us are having more trouble today focusing on, we want to make sure that text is as readable as possible. So here we have some, made up, not real text, but what we want to show is that this is kind of a simulation of what happens when your eye foveates on the first word, and then you kind of see the following words, and then the rest is kind of blurry before you move your iris to con. Now let's put in some hyperlinks. When you do that, they're kind of showing up, not terribly, but now let's put in some icons, and then if you look here, it's sort of interrupting the flow, and now we put these word scale visualizations. It's probably just not helping. So this is kind of more of a PSA until I have the proof, but I think to support fluent reading, legibility of long spans should receive high priority, and insertion of non-alphanumeric visuals into paragraphs may impede fluent reading. Yeah.
Word scale visualization is not a thing.
There's a set of researchers that write papers over and over and over about this, and I get to review them. It has been tried a little in, say, financial data. Where you'll see it in the most likely is like stock ticker data. They might have it kind of up or down a little bit, which I think is fine there. But people are putting like these big circles with a 1, like 0.1, 0.2, or icons like I have a user interface design, and now here's like the part that, has the input, and they'll put the little piece of input, and here's this other part, and then people will stick that right in the paragraphs. It's very common in HCI database and visualization papers. I can send you examples. Could be. We're going to be studying it. There's nothing in the literature that looks at this now. The only thing we have is one piece of literature on hyperlinks showing that it's distracting, and another piece where they put an emoji at the end of a single sentence by itself. And if the emoji echoes the word, like if you say, let's get a beer, and it's a beer emoji, then it's fine. But if it's incongruous, then it's not. But it needs more research. It's, again, something that doesn't get looked at. And I've done some extensive literature searches. If anybody knows of it, any literature on this, please get in touch with me. There's a lot of work on saliency, and that's very complex, which feeds into the next topic, which is cognitive models for combining text and visuals, which again, I'm really just getting into. But overall, the work that has looked at how are the two perceived together is conflicting, and this is not well understood, and certainly not for visualizations. People have looked more at multimedia like images versus visualizations and text. So there's competing theoretical models. So the most popular one, the dual coding theory, states that there are two cognitive subsystems, one visual and one verbal, that operate independently and simultaneously process both modalities to construct a strong mental model and enhance memory. So this theory is, give me both modes, your brain can handle it, and they will combine it just fine. And a lot of this has been promoted by the long career of Richard Mayer, who has studied multimedia and written several books about it. But what he is really focused on are designs like this, where it's physics that can be shown visually, where it's really important to show the interaction of things. You know, this pulley pulls this thing, and so you need a picture, and then the text augments that by explaining the picture. So he's done extensive research on combining language and images for explanations of processes. And as part of that research, he proposes the dual channel version of the dual coding theory. And in the dual channel model, it assumes there are these separate systems for processing pictorial and verbal information. Each channel has limited capacity, limited by working memory. And meaningful learning involves actively building connections between the two. So that's the claim. So we have, here's the diagram from his book. We have words and pictures coming in from a multimedia presentation. Words go to both the audio and the visual cortex or memory. I guess that's the perceptual system. Pictures just the visual. Words are selected, they make sounds, images, I don't know, stuff happens here that interacts with working memory, storing these things. There's also long-term memory that allows you so this kind of bottom up, top down, you have schemas to instantiate or things, knowledge in the world to help you recognize things. And the magic happens here. They're integrated in this circle somehow. And my argument is we don't know anything about that circle. Okay, so that's the claim. And if you buy it, it kind of helps explain this result, that the two belong together, that people can look at the chart, they can look at the text, they do bottom-up, top-down understanding, and they work together great. It kind of helps explain. It doesn't explain all of it, but helps explain it. Okay, but on the other hand is cognitive load theory, which claims that since working memory capacity is limited, simultaneous transmission of inputs via several channels will overload a learner's memory capacity and negatively affect comprehension. So it's basically saying the two compete with each other. And there's results in the literature that's supporting each of these. It sometimes depends on the task and the design. It's just all over the place. And so I would say it's just not definitive. But if we can talk about why do some people prefer text alone, is it personal preference? Is it familiarity, fluency, literacy? Or is it something about working memory capacity, or all of these? And the cognitive load theory provides evidence that from some studies that learners with both low visual and low verbal abilities did worse when both modes were provided and just would prefer, say, text alone. So that's a possible explanation. But it could be preference, it could be familiarity or fluency. So we don't know the answer. Okay, and then a newer theory comes from Les Padilla et al., which I think is extremely interesting, where they look at dual process theory. So everything has to have a dual in it. But this is the Kahneman and famous Kahneman and Tversky System 1 and System 2 idea, where System 1 or Type 1 reasoning is automatic decisions. It does not require controlled attention. I'm sure everyone's heard of this. It's in the popular literature and so on. And Type 2 is contemplative and effortful, uses significant working memory and cognitive control. So it's kind of the automatic thinking versus the fast, emotional thing, whatever, or the perceptually biased versus the thoughtful, top-down sort of thinking. And what she's done is she's applied this to understanding visualizations by incorporating it into Pinker's theory. So let's take their example. Say a student is given this, a person's given this question: is the average value of A and B closer to 2 or 2.2? And if you use System 1 thinking in this framework, that would predict you would select 2 because you kind of put this line and it looks close to 2, and so we're going to say 2. But to get the right answer, which is 2.2, You've got to use system 2 thinking. You've got to look at the two values. You've got to carefully see the first one's 2.4, the second one's 1.9. You got to add those together and divide by 2, and then you're going to get 2.2. And you have to override the system 1, like where you want to go. So it's a lot of cognitive work. So she illustrates this by integrating it into actually Pinker's very old 1990 theory of information visualization processing, where you have a visual array that comes in, has bottom-up attention, a visual description is formed, it gets matched to some prior schema about visualizations, instantiates it, makes a message, and then working memory plays a role if you want to figure out the relation between these two, and if you're doing the system 1, you just sort of do this quick visually based, spatially based decision-making in, say, 2. Versus if you're going to do the type 2, the slow decision-making, you actually start with top-down attention in addition to bottom-up attention, kind of look at these values, do the math, do some more math, and use working memory and come up with the right answer. So I think this is an interesting way to think about these things, because I think that perhaps this might explain this result about the predictions not being affected by the text annotations. So it might be really more the system 1 parts really dominating the decision when you have to make this gut choice about which is higher, which is going to be higher. And even imposing this top-down stuff with the text, it would require overriding that. But I don't know. That's just a thought. Okay, so I've talked about how to combine text and designs. What do cognitive models tell us, or touched on it very briefly. And now, because we have to, we'll talk about how does this relate to VLMs. So, there's a lot of words for this. There's multimodal language models, visual language models. I've seen VL, ML, all kinds of acronyms. Before I talk about this part, how many people in the room are familiar with how multimodal language models work kind of at the medium level? Only a few. Okay. I wasn't until recently, because it's really hard to stay caught up. So I recently read a bunch of papers to get a basic idea. Because what I wanted to know was, how the heck do these things recognize text plus visuals? And how do they reason over them? How are they so good at doing what they do? Like being able to convert a data to a visualization via a command, like create a visualization of the data in the attached file, which they can do. Or here is a visualization. What question should I ask about it? Or what are the trends? These things are great at pulling out information from visualizations, describing visualizations. They're not 100% right all the time, but they are amazingly good. So how does that work, especially with the two together, the language and the visualization? Well, remember I showed you this dual channel model from Meyer et al. And if we kind of tweak it and make it look like this, all I've done is, I've had an LLM actually modify it for me in the style of LLM architecture models. And it took many queries, but I got it. And so we can kind of see, we got the inputs coming in, we got something happening, and we have some magic here where it integrates. So what I wanted to do is sort of think about what's the relationship between these two. So here is a standard diagram for how a visual or multimodal language model works. So what do these things do? I'm going to kind of assume people know what transformers basically do, but do multimodal transformers mirror the dual channel model? Is kind of what I'm asking. And what happens when they combine the text and visuals? Like, what the heck is going on? So here's an example from the Flamingo model. And what they do is they give the model input where they'll have an image followed by some text and then a thing that it's supposed to output. Image, text, thing to output, image, text, and the missing output. So it's supposed to say like a plastic flamingo here. And here's the representation that gets fed, well, sort of, the raw representation that gets fed into the computer. You have the beginning of sentence, image, an image, some text, where it has a question and an answer, and an end of I don't know what C stands for. And then they have 3 of these. And then the very thing that's left open is they don't have the answer for this. So the input is this combination of vision plus text, and the output is text. So this is a standard transformer-based large language model architecture diagram. And you don't have to know what everything does here to follow what I'm trying to say. But the input is a text prompt that gets chopped up into pieces, tokenized, and gets embedded, put into a vector of numbers in a very high dimensional space. And these are then fed into the standard decoder block of the transformer, which does all the interpretation. And then there's output vectors like for the answers, like no, it is not, or something like that. And each of these blocks is a piece of a transformer. Okay, and here is the standard vision transformer, where it's very similar, but instead of text, we've got some images. The images get chopped up in various ways, and there's a lot of variation on how that's done, but the common one today, my understanding, is to make little patches of the image of all sorts and mix and match them, and then you have to really reduce the dimension way, way down so that it can be fed into this thing. But they're very similar. And looking at a little more deeply, we have some text. LLMs are cool. They get looked up in a vocabulary dictionary, turned into these vectors, and, came this way. And then, text comes in. This is a tokenized text. Here's the embedding layer, and here are the vectors that come out. And similarly, for the images, they get turned into tokens. Okay, so there's 2 main general architectures, my understanding, for these multimodal language models. In the first, it's kind of sometimes called the unified embedding architecture. All the visual stuff is processed to get embeddings of the visual tokens. The text stuff is processed to get embeddings of the text, and embedding is just a word for a vector, a very high dimensional vector that compresses a lot of the information down. And then they are simply concatenated, meaning one is followed by the other and fed as input to the model. And it kind of, after that, is trained as before, as just like a standard large language model. So they're next to each other. Okay, so what do I have? Yeah, transforms the visual input to have, and it's very important to transform the visual input to have the same dimensionality as the language embeddings. Because, for a given image, there's, it's huge. There's thousands of pixels, and then there's like 3 words. So the words are sort of outgunned, so they really deeply reduce the dimensionality of the images. And then they concatenate this on. The other model architecture is called the cross-modality embedding architecture. And what this does is it first of all processes the vision. And again, there's many different ways to process the vision input. Does the text in a standard way and feeds it all into this block called cross-attention. And for those who know this stuff, the language model layers are kind of frozen, and then new active layers are interspersed among them that the cross-attention develops, so that you don't lose a lot of the power of the language model. But if you look at that, now we're sort of seeing something similar. I kind of think this cross-attention is kind of the magic here, or I'm wondering if there is an analog between the 2 of these. So then that makes me wonder, what's really happening with this? Okay, so first of all, standard self-attention versus cross-attention is kind of what happens in these decoder blocks to help the large language model learn, across the layers how to process information. And basically, don't worry about the details of this. It's just the main thing is you get some input tokens in. It gets broken into kind of 3 matrices, and then they get combined and get an output. And this is how the learning happens, by changing the values of the matrices across the different layers. For the standard self-attention, it's for letting the words within a sentence look at each other. So for example, if you said, John took it to the store, you want to have John and it get attended to each other, for example. Versus cross-attention, it allows the information to flow between 2 different sequences. So this could be, say, image, and this could be the text, and then some of the matrices are combined. So that's the essential difference with cross-attention, is the information is coming. It can be for translation from two different languages. For the image text model, it's for the image being combined with the text. So here, a little deeper dive from the Flamingo paper, because I think it's just super interesting. So Flamingo will have as input, say, a web page with text followed by image, text followed by image, and it kind of assumes that the text is modifying the image that comes after it, say. And so then what they do is they process this text. They have image, tags, and text. So we'll have cute pics of my pets, then the image, my puppy sitting on the grass, then an image, my cat looking dignified. Okay, that gets tokenized, and they actually, so now we see the text tokens here, and we see these little numbers here, which are weights, which are basically hide all of the tokens except for these. So when I'm looking at my puppy sitting in the grass, only look at the puppy image. And when I'm seeing my cat looking very dignified, only look at the cat image in this mask cross attention, because they mask out some of the words. And this is partly so that the text only looks at the relevant image and not the image before, but also so that the text doesn't kind of dominate everything, is my understanding. So it's very deeply interwoven in this very interesting way. And this is different for other model architectures. There's also people that have tried to look at what is learned in the different layers in these multimodal large language models. Where is the text having a role? Where are the visuals having a role? So this is a schematic based on the lava models by this one piece of work. It's simplified because it's only showing 5 layers, and these things usually have like 32 layers. But what they're showing here is the input. This is for the unified embedding architecture, not the one with cross-attention. But we're seeing some images coming in here. These are the image tokens. Here's the text tokens, and this is kind of the answer token. And what they're saying is at the bottom levels, some number of levels, the model propagates general visual information from the whole image into the linguistic hidden representation. So it's kind of talking to that. Then in the middle, selected visual information relevant to answering the question is transferred to the linguistic representation. And then at the top, it's kind of got its answer. It's already done the integration, and then it kind of makes the answer. So overall, the papers that I've looked at so far find that the first layers and the bottom layers and the top layers rapidly kind of consolidate the visual information, and the middle layers kind of are doing a lot of the semantic processing in some general statement. So does this help inform text plus viz for humans? I have no idea. But when you think about what are these things actually doing, I mean, I think thinking about this juxtaposition maybe is kind of a helpful way to consider it. Okay, so to recap, I've talked about combining text and visualization. I've shown that more text is better for visualization, assuming it's proper text. Cognitive models are lacking for explaining this interaction. And MLLMs are kind of interesting for thinking about this intersection. There's other directions like spoken language, accessibility, linking visualization and documents, misinformation, multilingual, and visualizing text itself. But I don't have time for that. Thank you for your attention. And I'm happy to take questions.
Yeah, thank you so much for the great presentation. I really enjoy hearing about all the results. I'm especially intrigued by when you're showing that some people prefer text, some people prefer visualization, more people prefer like visualization plus text in certain ways. I wonder if you find if you find this like kind of percentage change under different contexts. For example, if they are like looking at text versus visualization, like when reading a book versus when they're like looking at a PowerPoint slides, things like that. Because I just recall like when we were doing presentation, we always hear this like guidance that we should avoid like putting too much text on a single slide. So I wonder if like that kind of preferences will change depending on the context.
Yeah, PowerPoint slides in general are just super interesting. So there's definitely, there's this other model I didn't talk about, which is cognitive fit theory, which is that the language and the visuals should align and the visuals should be appropriate for the task. And one of the biggest mistakes in PowerPoint slides is having the words not match what the person is saying. I try very carefully to have them match, although I add more words. I'm sure I made some errors in that. But when they are disharmonious, then it really splits the attention. It's very problematic. The thing, the advice about don't have too much text on a slide. You definitely, if people are just trying to read while you're showing bullet points, and they're going to be distracted. So that's why you want PowerPoint ease, where you just put in the verb and remove a lot of terms that you don't need and rewrite the sentence many times to shorten it if you can, to make it more effective. But the other thing to keep in mind is when you're watching a slide, you have no control over the time. So a PowerPoint presentation is a lot like an animation. And we know with animations and visualizations that they really are very hard to deeply understand what's happening. And it's much more effective if the user has control over the time and can step through the animation. I mean, we've seen that. Many results show that. But you don't have that in a presentation. And so you're just necessarily going to miss some things. But yeah, overall, you don't want big blocks of text. Or if you do have them, you should read them, which is what I tried to do in most cases here.
Yeah, thank you so much.
Yeah. Hi, thank you so much for this talk. Super interesting. I find it very curious, going back to the earlier part of the presentation, that like many participants in your study actually preferred the heavy text plus viz, but I think it was some of the later findings suggested that they only took one thing away. Like if it was just the text, they would just memorize or like remember the key statistics, or if it was the viz that they focused on, then it was like the overall trends. And the later theory about how this presents maybe more cognitive load seems to support that. But I guess I'm curious about the situations then in which this would you would want to trigger this like system 2 type of thinking, such that they might actually try to integrate these two things.
By the way, the System 1, System 2 paper does not address text at all. It's totally missing from that. It's only visuals. So that's a way it needs to be extended. The different conflicting examples that I gave, I think in some, the takeaways are different than the predictions. And so in the takeaway case, they're trying to understand some data they've been given. And also we gave these in isolation. We didn't give surrounding text for the charts. And so having some explanation of what it's conveying can be helpful, versus in the prediction one, where especially because we designed it to have no right answer, people really have to just go on what they're seeing visually, and it's the language isn't influencing that overall perception. Now we could have, the text we used was very anodyne. It was like, green is great or whatever. It didn't actually add any information to it. I think even in that case, it'd be hard to have something that would still influence people's perception, other than text saying, in the end, blue won, that would probably influence people. But other than that, yeah. So I don't think, again, my point is that this is still very underdeveloped and we don't have the answers, but it is often very context specific too. And a lot of the studies where it is conflicting, like with the dual channel, I have slides, I didn't show one, where, actually, let me really quickly go there because I have it as a hidden slide, because I had to edit a lot of stuff out, but let's go, because it's a good example here. Sorry, I know it's there. Okay, so this is a classic paper in cognitive fit theory where they're like, okay, we're going to have some charts and we're going to have some tables, and the charts are going to work well for the spatial tasks, and the table is going to work well for the symbolic tasks, and they were wrong. For spatial tasks, the charts were faster, but they were less accurate than the tables. For the symbolic tasks, the tables were both faster and more accurate. So it's like undermines it. On the other hand, it's not a very good chart. I mean, I'm not sure if it was black and white or if that's just how it was printed in the paper. So I think for a lot of these things, it really depends on the actual details of the design. And so that's why I think it's just really hard to draw conclusions right now. So I hope that answered your question.
Yeah, this is great. Thank you.
Okay, so I think we're at time, or do we want to take one more? Just one more? Okay.
This
this is like a very simple question. Thank you for the talk. When you were talking about like getting distracted by like having like random images within the text and things like that, I found myself reading much faster to get to those places. Have you seen that like also like where people are on purpose including figures in that like in reports or readings to basically make people read faster, and like have you seen that in general or no?
That's really interesting self-observation. We are just starting the studies on this. The people that have promoted this kind of bury the study. I think the studies are negative. So my recommendation for something like that is to just use inline charts, between the paragraphs. Just have the text, put the chart, finish the sentence, then start another paragraph. That's what I actually think people should do if they want to do that. But I don't know about people reading faster to get to it. Personally, I find my eyes going all over the place because I kind of want to look at it and I kind of want to read and I don't know where to go. But it'll be really interesting because we're going to do eye tracking to see what the scan paths are.
Thank you, everyone. Thank you, Marty, for this amazing talk.
Thank you.